there's some, depending on the catalog, there are some which will give you cutout views, so you don't really have to do a lot. You're just basically modeling based on what's in there. So the first milestone is that basically creating solid models for the parts. This is an example. Obviously, there are things which are not manufactured by a gearbox manufacturer, like bearings, fasteners, keys, and so forth. So those you don't have to design them. I think these days you can find solid models for almost all of them from the suppliers. What you have to do is basically flanges, shafts, housing, things of that nature. Right, so that's the first milestone. Modeling a gearbox, like a two-stage gearbox, and all the components. If you look at what I posted, so that's your milestone one. You will the parts that you basically model, like as I said, flanges, shafts, and so forth. You will apply GD&T, surface treatment, anything that would be necessary. You have to do a lot of research on this to figure out what happens with a typical, gearbox. For example, the shaft will probably be case hardened when they meet the bearings, or there could be a specific requirement for surface finish when seals are there. So there is some element of research into this project, which you'll basically have to do. The parts that you don't need to model are the parts that are mass produced. They're made in millions, right? So maybe that's a good way to look at it. For example, if I go back to this, like bolts, right? Picture is not very clear, but here you have bolts, for example, bearings. These are, even the company who makes these gearboxes, they're not going to manufacture bearings. They're going to source them. These kind of, forgot the exact name, these clips that prevent things from moving axially, keys. These are the type of things that the manufacturer of these gearboxes are not going to manufacture from scratch. Seals are the same way, right? So these are made by other people. So out of these gearbox, what we're talking about is the housing, flanges, shaft. Like this gearbox, this is a single-stage worn gearbox, so it has only one shaft. Pretty much that's it. So whatever shaft is used. The gears, again, you don't have to model because usually there are specific, specialized companies who make gears for people. Right? I hope that answered that question. Are the groups assigned? Are the groups assigned or do we pick them? That means, Michael, you're one of those people who's not in a group. I think around 60 odd people are already in groups. So the groups until tomorrow are self-assigned, like you pick people you want to work with. There's a discussion forum on D2L that you can use if you want to join with. There are a few groups which have 3 or 2 people in them, so they have to go up to 4. So you can join those people. But yes, that's how the groups are. So as far as the rest of, I guess, the timing, I put the first deadline for you is end of February, basically. That should give you enough time to do the modeling and what's required for project one. I guess when we get closer to second, third, and fourth milestone, I'll discuss a little bit more. Any question? Again, when questions comes up, like general nature, please use D2L. That way we can have a efficient process for answering questions. Was there anything else I want to say? No. All right, so we can go back to what we were doing, which was reviewing GD&T, and obviously you have to use what I'm covering right now in these lectures in your individual projects and group project. So that's relevant to both set of projects. So what we were doing was we haven't looked at the individual geometric tolerances yet. We were looking at modifiers. There's a whole bunch of them, and new ones were introduced in 2009, and I don't think they added anything in 2018. But for now, we are just looking at the material conditions very briefly. We'll come back to that. I'll talk about maximum material condition and least material condition for features of size. Again, you'll see more examples, and we'll repeat some of this information again, but that's what I want to talk before. Now, this business of material condition also applies to datums. Remember, we said there are two types of datums, the ones which are size feature or feature of size, and the ones that are not. So if you remember, a surface is not a feature of size, but can be a datum, whereas a diameter of a pin could be datum, but also feature of size. So because some datums have size, you could have material condition attached to them. It used to be that RFS and MMC were applied to datums, but since 2009, there's new terminology. So material condition, when applied to datum, which is what I'm talking about here. So look at this in this example, this central hole is a datum. So it's datum B, but it could be with symbol M or without symbol M. So instead of maximum material condition, the new terminology is maximum boundary condition. So this applies only to datums. Right? Least material condition is least boundary condition. And RFS, which was regardless of feature size, it's called regardless of boundary condition. All right. So these have changed according to these. All right. So used the wrong terminology. So it's maximum material boundary, sorry. Maximum, the condition is not there. So MMC has become maximum material boundary. Then we have least material boundary, LMB. And the last one, when the size is doesn't do anything, is regardless of material boundary. So this is the terminology. So it used to be MMC, used to be LMC, and used to be RFS. So this has changed since 2008. Now, what does that have to do with anything? So what is the difference whether that datum B has the letter M around it or not? So I'll just talk about M. The other two basically becomes clear. So the red item in this slide is your gauge or the mating part, and the green is the actual part itself. So maybe it's easier to start with when we do have the M attached. So when M is attached to the datum, that means that the datum, which is this pin here, represents the datum of the part, is a specific size. And the size is the maximum material condition of that datum. So basically, the part might be loose on whatever it is assembled on. So if this is the gauge we're checking the part, you can move it around, and if it fits over the datum and over the 4 pins, is acceptable. Whereas if that M doesn't exist, which is the situation here, there has to be contact between datum B and the part that attaches to it. So when would you have contact in that central feature? It's either you have something like a chalk that you can see in the drawing, in the picture, like a 3-jaw chalk, or if it's a press fit. So you probably can guess that when the M symbol doesn't exist, you have a way more restricted assembly condition, right? So the part has to be very specifically produced to pass inspection and to fit onto what it is fitting. Whereas when we have the material condition M, you have wiggle room, right? So the part can move around, and then you connect it or put the bolts through or assemble it. Right? Somebody wants to copy these down. So yeah, maximum material boundary, least material boundary, and regardless of material boundary. So I don't want to get too bogged down in this right now. We'll come back to this a few times. I just want to make sure that I'll introduce it so that when you sit in the drawings, we can go back to it. All right. So with that, with those preliminaries, we can start looking at geometric characteristics themselves. Again, as I mentioned before, these are grouped in 5 different groups, and we're going to cover them. There's like an order or priority to them that you will either or you will see as you go through. So we start with tolerance of form. So form means that external, basically characteristics of surfaces and edges and so forth. Although some of these will be changing. So form tolerances, we start with the straightness, right? So the symbol for it, as you can see, is a straight line and a number. The straightness, let me ask you this, and you can raise your hand or write in comment. Do you think straightness of a line or an edge, could it ever have data? Does it make sense for it to have a data? Okay, one chat coming. In micro scale, maybe. Forget about the scale, at any scale. What does it mean to have data for tolerance? Maz, go ahead.
The reference for other stuff or other dimensions.
Yeah, with respect to, right? So, Jagdishwar, is that what you're going to say?
Yeah, I was gonna say that you can't really have a date on
Yeah, go ahead.
because data's like a reference point.
Yeah, so exactly, right? A data means reference to something. But the straightness, like if a line is the straight, right? It doesn't have to be with respect to anything.
Yeah, exactly.
Yeah. So exactly because of that reason, there is no datum associated with a straightness, right? So what does it actually mean? What it means is, for example, in this drawing, you have a part, and there's a straightness of, there should be a point somewhere, a straightness of 0.005 inches or 5 tau indicated on that surface, right? So even without this tolerance, there is a limit on how straight any point on the top of this has to be, right? So if this is the part, right? We are talking about lines across, right? So let's say if I traverse a line on the surface, just one line, what Torrance is telling me is that this line on the surface has to be bound within two lines which are not more than 0.005 inches apart. Okay, so if I trace a line on the surface, imagine you have a probe crossing the surface, right? So like a needle of some sort. As the needle crosses this surface in that direction, it cannot go up and down more than 0.005. That's the meaning of a straightness in this case. Now, which line? Any arbitrary line. But at each case, I have to zero it, right? So if I pick an arbitrary line and pass through, the difference between the lowest and highest point cannot be more than 5 tau. That's the meaning of a straightness, the way it's shown here, right? Now, even without the straightness tolerance, there is a little bit of control over straightness of any line on that surface. Can anybody guess what that is? Like how much? So imagine that this didn't exist, right? Imagine this didn't exist. What would be the limit on how much a line traversed on top of this surface can change or be out of a straightness? Or is there any limit to it? Go ahead. I don't know what your first name is.
Would it be the tolerance of 0.005 for the other dimension?
Yeah, so exactly. So it will be controlled exactly right. So basically it would be what you see from the tolerance of size, right? So this thing is acceptable between 870 and 880, right? So any given line could be basically anywhere there. So this would be an acceptable part. So the only difference here is that the difference between these two lines, or the distance between the peaks and valleys, can be 0.010 tau, correct? So without this flatness tolerance, straightness tolerance, you still have some control over the straightness of the lines on the surface, but it's a wide range. If you want to control it more tightly, you put a tolerance of 0.005. So would it have made sense if instead of straightness of 0.005, we had a straightness of so let's say raise that. So instead of 0.005, would it have made sense to have 0.010?
I don't think so.
Yeah, doesn't make sense, right? Can you
Yeah,
give us your
because
reason
it's
why not?
redundant.
It's redundant, right? Exactly. So because the dimension, the tolerance of size already does that for you, right? So you don't need the flatness tolerance. So for this flatness tolerance to make any sense, straightness tolerance, you have to make it tighter than what it is there already. Okay. Do you have a question? Somebody's raised their hand. Yeah. Okay. So that's basically what straightness means. You have to be careful that it does not control orientation, right? So you could have that top surface could be tilted, right? Within the tolerance of size, right? So one end could be, what was it, 870? One side could be 880, and then you would have the edge looking like this. So this is still acceptable, right? So what you're controlling is the straightness. That's why it doesn't have a datum. The orientation of this doesn't matter, right? So it could be any orientation. So we're not controlling what orientation it is. Now, this was straightness applied to a surface. This is an example of it, right? So here I have a pin with a straightness of 4 tau applied to the surface. So that would mean any line on the surface of this pin cannot have peaks and valleys which are separated more than 4 tau. this might be a better picture to show it to you, right? So the shape could be whatever it is, as long as the differences are not more than 4 tau. When would this be useful? This is an example of when this would be useful, right? So you have two rods, and this stage is basically moving back and forth. So if you don't want, as this moves back and forth, to have any wobbles, you want to control the straightness of lines of contact, right? So this would be a good application of the straightness of surface line. All in all, the applied to a surface straightness is not very commonly used because it doesn't have a lot of applications. One place it has very good application is when you want to control the straightness of an axis of a cylindrical object, like a pin, right? So here we have a hinge. Obviously, it's important that this is straight, right? It doesn't have to be straight with anything, with respect to anything. It just has to be straight to work in this application. So how do we control the straightness? So in this case, it's not the surface that's important. The axis of this pin is important. So you can do that with this application of the straightness. So this is a straightness applied to a feature of size. So it's not applied to a surface. It's applied to the diameter of this pin. An interpretation, because this is applied across the diameter, it means that applies to a derived center line, right? So we have a derived center line in this case. And the interpretation of 4 tau is that there's a cylindrical tolerance zone, and the axis of the center line, this derived center line, has to lie within this tolerance zone, which has that diameter of 0.04. Now, you could have that without MMC, or you could have that with MMC. The main difference is that when you have MMC, you'll see that we'll talk about this later on. You can actually make a go-no-go gauge, kind of a functional gauge, and test this with a gauge. Whereas if you don't have that, you have to find other ways of inspecting and making sure that the part matches the tolerance. Now, one thing you have to recognize that you still are bound with size limitations, right? So if this pin is between 1 and 1.02, any of these lines cannot be more than or less than minimum and maximum sizes, right? So at any cross section, the size limit applies, but the center line could be within the tolerance zone, which is a cylindrical tolerance. So in this, for controlling the straightness of pins, things that they don't have any datum, the straightness is a good tolerance. Now, this is not allowed, right? So here they've applied a straightness to a non-cylindrical object, and you cannot do that because this basically creates a two-dimensional surface, and you cannot control that with a straightness. we have flatness for that purpose, and this is a wrong application of the straightness. Now, as I said, if you have that M there, you can make a gauge. Sorry, not in this one, this is not acceptable. Here, if you have that letter M, you can make a gauge for inspecting straightness. We'll discuss functional gauges after we review all the GD&Ts. But if you don't have, so in a case like this, which is regardless of feature size, you have to actually inspect or measure parts one by one, right? So this tells you the difficulty of measuring straightness. So can anybody guess why this is hard to do? So let's say I wanted to inspect this for a flat surface, like the first part that we did, right? So we want to inspect the straightness on that surface. Can you guess why that's a difficult thing to do? Time consuming, but why? Not really the equipment per se. Remember, this doesn't have data. The way this part is set up right now, it does have a datum, correct? Because it's been set up on these points. So in a way, this has become data for your inspection, right? But you don't have a datum, right? So you have to kind of eliminate the effect of the fact that this is setting up on parts. So what you need to do is level the part, right? And leveling this part, so these cannot be the same size. So you have to level it so that you get an optimum surface, and that's very time consuming, right? Because there is no, you just want to tilt this until you get as flat a surface as possible, and that requires trial and error. Even if you have a CMM, that is still requires additional steps. CMM is coordinated measurement machines, right? So because the tolerance itself doesn't have datum, it's kind of hard to inspect it. Right? Again, you see it here. If I try to, so this is a cylindrical part. If I want to try to inspect this line on it, I have to inspect just the line on the top surface. But because I have to set it up in some sort of arrangement, these become datums if I'm not careful. So again, you have to kind of tilt it until it's optimum flat or level, and then do the measuring. There are some tricks that you can do. This is arrangement useful if the straightness is applied to feature of size and therefore applies to a derived, as we said, applies to a derived center line. So if I want to find out whether the center of this cylindrical part is within the tolerance or not, this is an arrangement can be used, right? You have two dial indicators and move them together, and the difference between them is basically deviations. So the way it's shown here, so 003300 is basically perfectly straight. Now, if there's a difference between any two of these readings, you just monitor that, and that has to be within a tolerance. The moral of the story is that without maximum material condition, which allows you to make a gauge, it's very difficult to inspect this tolerance. Go ahead.
In the previous example, what surface are we trying to make level here? You said you have to tilt the part to.
Yeah. So let's say the tolerance was applied to this top surface, right? And you want to remember, so this was where the straightness was applied, correct?
Yeah.
So now I have to set this part such that this surface is which I'm inspecting is level, right? Independent. So this surface, I wanted to make it level, independent of the bottom surface, because it's not referenced to that. You know what I mean?
Yeah.
The way it's right now, it's basically, it might be level on the bottom surface, but not level here. Make sense?
No.
Why not? So let's say this is a perfectly flat surface, right? And these three are perfectly the same size. They're all 10 millimeter, right?
Yeah.
Then, because there's only three of them, this bottom surface would be perfectly flat on them, level on them. Do you agree?
Yeah.
But that's not the surface I'm inspecting. I'm inspecting this surface. So the surface at the top could be tilted, right?
Yeah.
So I need to make this flat, not the bottom surface.
Okay. That makes sense.
Yeah. But in general, it's not an easy task, and that's why when we get to that point, it's not a good tolerance to use, especially without M. So it's a good tolerance to use with pins and cylindrical objects if it has that M in it. We haven't talked about when you decide to have M or not M. We'll get there, but if you see this tolerance without M, you may want to talk to whoever put the drawing and see whether that's really needed, or because it makes a huge difference in inspection cost. So that's the straightness. The next one we'll talk about in the form tolerance is flatness. So as the name implies, this is how flat a surface is, right? So we're not talking about the one-dimensional object, which is a line, which was what a straightness controls. This is a two-dimensional surface that we are going to look at. Now, what are the applications? The application of flatness are a lot more than a straightness, right? You can see in the picture, one is when you have sealing surfaces, right? So if I'm two pipes with flanges and there's a gasket in between them and you want to have a sealed connection, flatness becomes important, because if the surfaces are not flat enough, you might not be able to get a seal out of the connection. This becomes especially more problematic if you're dealing with gases rather than liquids, right? So any places when you have joints, things come together and they have to have positive sealed connection, flatness becomes important. Now, you probably know about how we characterize surfaces. When you look at an engineering surface, depending on the level of detail, we have different quantitative way to look at it, right? You probably, I don't know if you remember roughness. Roughness is basically the features of the surface at almost microscopic level, right? So at very small scale. Flatness is at a larger scale. So if you look at this simulated surface, roughness is these modulations, whereas flatness is these modulations, right? So when we're talking about flatness, we're talking about a certain level of size to the feature. This is what I found useful to think about. So what we call flatness falls into this order of magnitude, right? So these are caused by machine tools, tools themselves. So that's the inexactness of the surface based on those. Roughness and the different level of roughness is not what's controlled by flatness tolerance. So the symbol looks like this, and the interpretation is, in this case, it's applied to a surface. So that top surface can have peaks and valleys which cannot be separated more than 2 tau in this case. So you can think of it for a straightness, we looked at what happened to one line at a time. So we tested the line, and if there was not too much deviation, we accepted the part. Then you zero reset and you check another line. But for a flatness, you have to look for any out of tolerance feature over the entire surface, right? So that's what makes it different from straightness tolerance. Go ahead, Trey.
So straightness is applied to a line, whereas flatness is applied to a plane.
To a surface, exactly.
Okay, thank you.
That's the main one of the main differences. So as I mentioned, anytime you have surfaces contacting, you probably need some level of flatness. Otherwise, you will have wobbling, right? So you always, I'm sure, seen when parts are not totally flat, they rock or they don't sit properly when you join them together or put them together. So that's what we can control with this tolerance. So if you look at this part, for example, so this flatness surface controls the bottom of the part. So in this case, it's 1 tau. So again, what it means is that over that whole area, you could have up and downs, but they cannot be more than 1 tau apart. So whereas for straightness, we had to test it with 2 parallel lines. With flatness, we have to test it with 2 parallel planes. So 2 parallel planes, 1 tau apart. Can I catch the surface between those two or not? Similar to what we talked about straightness, the dimensions of the part already controls the flatness to some extent. So if you're adding flatness, it has to be tighter than the size tolerance, right? So in this case, we have 2.5 to 2.492. That's 8 tau difference. Even if you break it down for this surface and this surface, you still have 4 tau in each side. So 0.001 or 1 tau is much less than that. So this is an appropriate use of flatness. Again, can flatness tolerance have a datum? I asked the same question about the straightness, right? So could flatness have a datum?
Yes.
Yes, everybody agrees?
Would it be the
Go ahead.
parallel plane?
Sorry?
Would the datum be the parallel plane that you're using?
So you are saying also that it requires a datum, flatness?
Yeah.
You think, yeah. It doesn't actually, because similar to straightness, right? So we're not talking about, so flatness doesn't say that this surface A has to be parallel to anything, right? It just wants it to be flat, right? So to make a distinction, right? This surface, the top surface here, right, could be flat, could be parallel, and could be flat plus parallel, right? If it has to be parallel, it has to be parallel to something, right? So if I was talking about parallelism, of course I need a datum, right? If I was talking about flatness and, go ahead, Luca.
Does parallelism automatically imply a flatness measurement as well?
It does, but we'll get to that. Yeah, we'll get to that. The same way that the dimension does some flatness, parallelism does too. But we'll get to that when, right now we're not talking about parallelism part of it, right? But if I only want to, so if it was flat, if I was requiring this surface to be, Ruth, go ahead.
I had a question. I can wait until you finish your sentence.
Sure. So yeah, if I don't require flatness and parallelism, only thing I require is flatness, I don't need a datum, right? Because this surface could be flat at this orientation, right? And a similar surface could be, right? I can talk about flatness of this surface too, right? Without any reference to whether it's parallel to something or perpendicular to something. So basically, tolerance of form don't require any datum because form is not with respect to anything else. Go ahead, Ruth, you had a question.
That was my question. I was just going to ask if datums are just for form and not for things like, if datums are not for form.
Not for form, right? By definition, they cannot be, right? So if I say, is this surface flat or not? I'm not asking whether it's parallel to something, right? Just the flatness itself could be any orientation. So flatness basically doesn't have a datum.
So would you really just have a datum for position of a feature, location, or the orientation of a feature, and that's pretty much it then?
You're jumping ahead a little bit, right? But that's fine. So form tolerances, they're not going to have data, right?
Okay.
Location, so nothing, no datum for these. These have datum. They cannot be defined without datum. These could or no, like it's optional, like depending on the use. And these also always have. Okay? But I'll just remind you again as we go through. But form tolerances cannot have datum by definition, the way they're defined. Okay?
Got it.
Sure. Yeah. As I said, I'll repeat some of these as we get there. All right. So let me talk about one more thing, and then we'll take a break.
I just have a quick question.
Go ahead.
Regarding the object that you just drew. If you were to test the flatness for this, like if you were to measure it, you would have to level that surface, right? The top surface.
Exactly. Yeah.
Okay.
I'll show you there are some other ways to do it, but yeah, if you want to set it up from like this this direction, yeah, you have to like the easiest way is to level it and then measure how much deviation you have. I don't know how many of you are familiar with CMMs. You can also collect a lot of data, and then CMM algorithm, they can actually rotate the whole feature, like level it by software, you know what I mean? So if you have access to CMM or computerized data collection, you don't really need to physically level it. The algorithm can do it, right? They will find the optimal surface that goes through all of them and then rotate it until level and then they test it. 3D scanner. There are some CMMs which are kind of non-contact, scanners. So in a way, they're 3D scanners. But yeah, I'm familiar. I know that you did CMM in 322, but just reminding you. So yeah, if you're using CMM, you don't have to physically level them. If you're using dial indicators, then you do. Actually, you know what? Let's take a break. I'll come back and talk about the rest of the stuff. Let's take a 10-minute break. I'll be back at